Okay, we've hit the last part of the lecture, line spectra. Okay, another mysterious experimental observation that classical physics struggled to explain in the early 1900s was the phenomenon of line spectra obtained from gaseous elements. When light emitted by excited gas was passed through a diffraction grating, right? Scientists observed distinct bright lines of specific colors against a dark background rather than continuous spectrum as predicted by classical electromagnetic theory. Each element produced its own unique set of lines like a spectral fingerprint. That means if this gas is hydrogen, hydrogen produce some colors. If this gas is, for example, some other gas, it produce different set of colors and is unique to the type of gas, right? So hydrogen always produce the same type of colors, right? So we look at the emission line spectra, right? It consists of discrete bright lines of different colors on the dark background. So this is a typical setup. There's high voltage here, right? So to make this positive and this negative, right? Then this hot gas over here is actually excited, right? So the gas here, the electrons are excited to higher energy levels, right? So what do they do when they're excited? You remember they are unstable, so they'll drop in a very short period of time, right? In nanoseconds. So when they drop, they emit light. But remember that the spectrum is discrete. That means it looks something like that, right? So if you get excited to this level, right, when it drop, it can only produce certain frequency of light or wavelength of light, depending on how you want to look at it. And therefore, only certain colors come out from this hot gas, right? Because there's no other source of light here except the de-excitation of electrons within the atom for this hot gas. Right, so high voltage is applied to low pressure gas to bring the gas atoms to excited state. As mentioned, it's unstable. After a short while, it starts to return to its lowest energy level. When they transition down, photons of energies correspond to the difference between energy level will be emitted, right? So due to the existence of discrete energy levels in the isolated atoms, these emitted photons will have specific energies corresponding to specific frequencies and wavelength, right? As I mentioned earlier, the photons are directed at diffraction grating, right? So diffraction grating will actually, this is the diffraction grating here, right? So diffraction grating will get diffracted in accordance to specific angles according to your wavelength and gives spectral lines when viewed through a spectroscope, right? This is the scope, right? It's a machine here. You don't have to worry too much about this. You can just, in exam, right, if you ever asked to draw this type of thing, you can just draw a label diagram. You just have to draw the actual whole setup, right? So you can draw things like this, then label, right? Something like that will do, okay? These spectral lines emitted by an element is unique to the element, right? So there's emission line spectra, right? So you need to know this, right? This is the table that shows you the energy levels, right? So this ultraviolet, this visible, this infrared as mentioned. Do you need to memorize anything here? Answer is no need to memorize anything here, okay? They are not, you're not expected to memorize anything. You need to know the process of calculation. Okay, so hydrogen, you can see you get these four colors, I think. Yeah, because of the Balmer series is visible. Yeah, I think that's all. Right, you can read the rest yourself. Not so important. Absorption line spectra is the opposite. All right, so it's produced by passing a continuous spectrum of white light through a vapor or gas. All right, so if I pass white light through a cool gas, what happens is that this white light that after passing through the cool gas go through the diffraction grating, right, you'll see rainbow because the diffraction grating will spread out the light to produce rainbow, and then you'll see dark spots. All right. So what happens is that as the white light passes through the electrons of the vapor, the vapor is gas atoms. So the gas will absorb photons of certain frequencies and get excited from ground to higher energy levels. Now, the photons that get absorbed must be exactly equal to the energy difference between the two energy levels of the gas atom, right? And yeah, that's why there are black spots. So these black spots correspond to specifically, right, the absorption that go from here to here, here to here, and here to here. So if this cool gas here is hydrogen, you expect that the black spots here are exactly the same as the bright spots here, right? These bright spots here, because if this gas also is hydrogen, because they have the same line spectra, right? They have the same uh, energy states of the electron, right? So it's either you go up in absorption spectra or you come down in emission spectra, right? So that's the idea, right? So that's why there's dark spots, right? So then you may ask, oh, but isn't it that the electron will get de-excited? But when it gets de-excited, right, the light doesn't come out to the right anymore. It may come out any direction, 360. So are there still some light particles that go to the right and come to this black spot? Answer is yes, but very little, because when the gas get de-excited, right, the electron get de-excited to a lower energy state, it will release the light that is equal to the black spot also, but it may not go in the direction of the diffraction grating. In fact, it's highly likely that it doesn't go to the direction of the to the right into the diffraction grating because it can go 360 degrees, right? And so you look at this is the emission spectra, and you look at the absorption spectra, they're actually the opposite of one another, right? You can superpose this on this, and they should nicely become the full rainbow. Right, so I think I've explained this. Right, finally, please do question 18, right, very quickly. Right, hope you have paused and done it. If not, please do so. Right, uranium energy of incoming photon required to remove electron from its innermost shell is this amount. Right, so this ionization energy. If the X-ray produced by electron transition from 2 to 1 is this amount, right, this is just 10 to the power minus 10. All right, as given here, you don't have to worry about this. Determine the wavelength of photon needed to remove an electron from E2. Right, so you just draw the energy levels, look something like that. E1, E2, infinity, right? So for remove atom, remove electron from atom is electron go from E equal 1 to E equal infinity, which requires this amount of energy. Then from E equal 2 to E equal 1, I can calculate the amount of energy associated with this wavelength of photon release, right? So hc over lambda gives me this amount, right? So this is the energy level from here to here. So what's the difference? Because I want the wavelength of photon required to remove an electron from E2 to infinity, right? To remove from the electron, I must go from E2 to infinity. So I want this energy level, which is this energy level minus this one, right? That's what I'm doing. And then the wavelength, you can equate the energy to hc over lambda, right? You can equate 16.93 to hc over lambda. Should be able to get the wavelength as 7.34 times 10 to the power minus 11. All right, with that, that concludes the quantum lecture. All right, thanks for your attention.